All right. Well, this is a basic talk on algebraic data types. Now, if you're already good at algebraic data types, you're welcome to stay. Maybe you'll learn something about a good way to present algebraic data types to your coworkers who are used to working with imperative code. But this is geared towards people who, when they hear the term algebra, might be like, I went into programming because I didn't want to deal with that. And I say that with all due respect because my mentor, who is someone who has helped me enormously in learning to be a developer, he's willing to learn algebraic data types, but he kind of went into programming not liking math. So I'm fully sympathetic to that position. I'm trying to cater towards that here. So my name is Keith Pinson. I'm a build engineer currently at Lucas Systems near Pittsburgh. We do warehouse automation. But I'm just kind of a general developer. In fact, one of the reasons I took that build engineer position was so that I could write F# and do fake build scripts and fake automation and F# automation tools and stuff like that. So I love algebraic data types. Before I really get started, I just want to say a big thank you to all the people who've put LambdaConf together. This is not like a formality. This is like from the bottom of my heart. This has been awesome. I'm sure you guys have been having a good experience too. So hopefully this will be a helpful presentation to you. Feel free to ask questions in the middle because my sole purpose is just to help you along in your journey. So what is an algebraic data type? Now, this whole talk is going to be about that. But just to give you a little bit of something to start with, and then we'll work into a fuller understanding. Sort of what is it from like a why perspective is it's a construct for enforcing the logic of the system you're modeling at compile time. And therefore, it is something that should matter to you because it actually has real application to the software you build, no matter what domain you're building for. I actually do use algebraic data types at my day job, and they help me build better software. Now, this is just a disclaimer in case any math nerds did decide to stick around in the room. There's no proofs here. There's a lot of what I do will just be kind of hand-waving. What I'm really trying to do is cater to the human factor and help you to get an intuition of how in the world something that is a data type could be mathematical or could be algebraic. So it really is a lot of hand-waving. I'm really helping you to I'm hoping to just get your intuition going on it. So apologies to the math nerds. Okay, what good are mathy types? Like, why would you want to introduce math into your programming? It just seems like a way to make it hard, right? Well, so let's start somewhere practical with something that we all have to do. We'll start with a real simple case. We'll go to just an idea of, say you're modeling the domain of an Italian restaurant. We'll just have a real simplistic domain here. So you take a statement from the domain and you want to model it in your code. So a real simple statement, an entree has a sauce. Now, if you were modeling this in some object-oriented language, say maybe C# or Java, how might you express this in a type in your code? As a property? Maybe something that looks like that, right? So that's real easy. Anyone who writes imperative code does this kind of stuff pretty regularly. Nothing to that. However, that also is not nearly enough to get you where you want to go as you're developing. So let's try to model a little bit more complicated statement. So let's introduce the word and. An entree consists of pasta and sauce. How would you model that? Just add another property, right? So that's kind of peanuts too. But here's the thing to realize. We've actually put logic into this type. Even though you don't see any ifs or elses, there's actually a logic inherent in this type. So we created a type to express a proposition or a truth claim, something that we intend to hold true about the problem we're modeling. Now, we're not concerned in the Boolean value of whether this is true. Actually, we always want it to hold true. We care about the logical structure of this proposition. So it's logic, but it's maybe a little different than the runtime Boolean logic that you're used to thinking about. So the point of this is just to say, look, you may not even realize it, but you're actually every day, even if you're doing imperative code, already encoding some logic into the types of your system. But when you're doing logic, the immediate thing you may ask after saying, oh, I have an AND, is do I have an OR available? Because saying AND for types, how could you write software without being able, in an imperative language, without being able to do what we just showed? You'd be writing in a pretty low-level language if you can't start wrapping stuff up like that in custom types, right? That's kind of indispensable for modern development in an imperative language. But what about OR? How might we say OR at a type level, and would that be useful? Well, I think it would be useful. For example, we could explicitly model the lack of a value. Now, we have a lot of bad ways of handling this in imperative languages, and I measure bad by the amount of pain and frustration and tears and dollars lost. So there's the ever-pervasive null, which even its creator admitted was a big mistake. Passing null, returning null, you have to be real careful. Or just throwing an exception. Say that you're writing a function that returns an integer and it's not nullable, but you don't have a sane value to return. So what do? You just blow up. That's not real great either. Or these other this API style at the bottom, which is a style you see a lot in the .NET libraries. Apologies to anyone who likes it. I really find this kind of a clunky way of just sort of working around the problem. So those are some examples of things that might be nice to solve if we had an explicit way to model OR at a type level. Another example is just a little extension of that, which is to clearly represent a finite set of possibilities that you know at the time you're building your system. So if we were really building software for an Italian restaurant, we probably wouldn't want to actually explicitly hard code what values are available for pasta or sauce or things like that, right? But even though I'm going to be doing that in my example. But there are things that we run into every day in our systems, where if your system is outside of a certain finite set, and it might be 2, it might be 3, it might be 15, but outside of a certain finite set of states, then it's just in an illegal state that really shouldn't even exist at runtime. So it's nice to have some way of telling the compiler, with respect to some aspect of my program, there's only this certain finite set of states I can be in. So that's just an idea of why we might want to have the ability to say OR in addition to the AND that we can already say in some imperative languages. Just as a side note, this AND is maybe not actually quite as strong as we would like it to be either, because what we really said in that type, since strings are nullable in C#, is that an entree might have a pasta and it might have a sauce. So it would be nice to make that statement a little stronger too. So I think it should be pretty clear that logical types are actually practical for our everyday development. But that doesn't really answer the question, because I thought we were talking about mathematical types, algebraic types, so what gives? So what I'd like to do then is sort of walk through an exercise to help you get an intuition of how the logic here and the algebra are actually the same thing. So let's start with something we can all agree on as mathematical. I'm not even sure a heckler could come up with something to heckle me about this and say that it's not mathematical, but maybe, I don't know. It is arithmetic. Good point. So from arithmetic, we move to algebra. And then from algebra, we sort of move to like completely abstracting the algebra. Now, going back to arithmetic, you probably remember these from grade school, and even if you weren't a particularly mathematically inclined person, they're kind of nice because you just have to keep track of what row and column you're in, and then there's a pretty predictable way of sort of working through them, right? So there's something that was mathematical as well. And you could do it, of course, with a different operation, such as addition. Now, what if we step this into algebra land by removing the numbers and replacing them with variables? Now, once again, even if you're not a particularly algebra-inclined person, as a programmer, you're probably fairly comfortable with this step. So we abstract up one level. Let's abstract up again. Let's abstract away the operation. Now at this point, we no longer even have to think of a, b, and x, y, z as numbers necessarily. Just think of them as entities over which you can have some operation. So at this point, we are soundly into the land of abstract algebra. So file that in the back of your mind, and let's return to our Italian restaurant. And let's build out our example a little bit. So say that these entrees that consist of pasta and sauce, it's a very small hole-in-the-wall restaurant, you don't have very many options. You can either get spaghetti, tortellini, or gnocchi, and you can get marinara or Alfredo. Now, my question here is not how many options are available, but what options are available. Now, before we try to actually answer that question, let's just analyze the structure of this problem a little bit. It's actually a logic problem, because I said spaghetti or tortellini or gnocchi, marinara or Alfredo, pasta and sauce. That has a logical structure, right? Once again, we're not concerned to evaluate whether it's true or false. We want to keep that true, and we're concerned with the actual structure of it. So it's a logic problem, but it's also an algebra problem. So if we take in that abstracted algebra table that we had already established was an algebraic thing, we find that this is actually a great way to map out the answer to this question. If you've ever worked in with some of those like little books that give you puzzles and quizzes and stuff, there's sometimes these problems that you have to work out by filling in tables. It's just sort of the same kind of concept. So this may not be what you're normally used to thinking about as algebra, but you can see how we got here from just abstracting up from the numbers, and how this same problem is both algebraic and logical. Now here's the interesting thing. If I take F sharp and I describe this problem in its type system, first of all, notice how concise it is, but also notice how similar this is to the slide where I said this was a logical problem. It's basically just a syntactic change, right? It's basically the same slide, just in a little more computer speak than in human speak. Those vertical bars are type level ORs. And the comma there is a pairing operation, just like we did with pairing together the sauce with the pasta in the table. Now this is actually algebraic data types here, but you see how they actually match that logical structure. But we can go further and describe this a little bit more to help you grab onto this even a little bit more. So what if we do go ahead and talk about like the number of possible things now? You will notice that the types that have OR at a type level exhibit a behavior somewhat like addition. This is where I really get heavily into the hand waving. If you sum up the number of things in each type, that's the number of possible values. So there's a behavior here somewhat like addition. And if any of you had Boolean algebra in your computer courses, you'll remember that there is a correspondence between summation and OR in Boolean algebra. Well, that's actually a more abstract truth than Boolean algebra. Boolean algebra is only one example of that. And we see a similar thing with the AND types, that they behave like multiplication. So if we just multiply the two numbers from the last slide here, that gives us the total number of values in an entree. So you see how there is a sort of structure like multiplication there. Now, if you actually want to dig into what's really going on here, you do have to go pretty deep into the math. But just grab onto the fact that the sort of intuition of the way this is working is actually true to the way it's working, even though I'm not going deep into the math. So we have algebraic data types. It turns out that algebra and logic is just another way of saying logic. And logic is, of course, something we have to care about as we're modeling the things we're modeling. Now, here's where you really hit the sweet spot. I believe that the sweet spot in all of computation is composition. And that's really where you get powerful simplicity from. And I'll be talking about this in my next section a little bit on lambda calculus and how the way lambdas compose together. And this is one of the things that's beautiful about functional programming. You can just combine things together. So say that we're doing some parsing. You find that when you're doing parsing often, you'll either have something successful, and so you'll have some sort of token to return as well as the remaining stuff that you haven't parsed yet, or it'll be some sort of failure, in which case you probably want to return some sort of error type. Well, we're able to wrap up this logic all into a type so that the compiler can actually enforce it. So this is safer than just putting if checks in the system, because you have to remember to put the if checks in, whereas the compiler will make sure that you always handle this the right way. For example, a consumer of this is not able to only handle success. You're forced by the language to handle both success and failure, which makes it a safe way of working with the states your program can be in. Now, there's just one more thing I want to sneak in as a glowing example of algebraic data types. And this is really just to illustrate like how much is going on under the covers when you have an OR type, and the contrast to an imperative language in which you really only have a weak form of the AND types. So this is the thing we were looking for earlier when we talked about having an explicit representation of a lacking value. It's completely type safe because you have to handle each case every time you handle it. And so the nothing there, unlike null, is not like a hole in your type system. It's actually strongly typed to whatever you've instantiated this generic maybe type to be. And then the just actually wraps it up if you have some kind of value. So this is actually F-sharp syntax, but Haskell naming, just because what I did was I then took this one line, put it in an F-sharp file, compiled it to .NET intermediate code, and then used a decompiler to create C# code. And here's the C# code I created. I don't intend for you to be able to read this. Actually, this is not the C# code it created. I had to strip out a whole bunch of different compiler hints and attributes that it had put in there that it was just kind of noise and I didn't know what they meant to me. I took out the equality methods, which were very nicely generated for me by the F# compiler. So there's structural equality on these algebraic data types since they're consistent in the way they're structured. The compiler is able to just know how to compare them. It's also able to know how to convert them to strings. And I removed all those methods so you could maybe just sort of faintly see the code here. I actually also removed a bunch of empty lines and combined a bunch of things onto the same line. And I think there's still like 47 lines of code there in C# for that one line of code in F#. And that's because rather than having the compiler handle all this logic, you're having to handle it all yourself. So that shows you the power that's there in an OR type in terms of reducing the complexity of your system to the base complexity of the problem you're actually solving. It really helps you to avoid accidental complexity. So in conclusion, I would just say to you, make friends with your compiler. When I was working in C++, I just thought of the compiler as someone who criticized me. Even when I went to C#, I still tended to think that way quite a lot. And it was just sort of like, this is just this hoop I have to jump through to be able to run my code. And that was the way I thought until I started using a language that had algebraic data types, at which point I began to actually use my tool to a lot more effect. It never makes sense to be using a tool and working against it. So I totally understand the appeal of dynamic languages. My first language that I really got into was Python. But what I found was, with algebraic data types, I'm actually, when the compiler yells at me, that's actually helping me. And I can actually, I don't have to write as many unit tests, and it gives me confidence in my system. So I have a very different perspective on that. And so, in conclusion, why would you care about algebraic data types? Well, it's because this algebra is actually logical, and therefore it's inherent in whatever problem you're solving. It doesn't matter what problem you're out there solving, there's some kind of logic to it. And these types can fit the solution very well. The other thing is because by being algebraic, they're computable. And this is the reason why the compiler is able to do things like auto-generate equality methods and string compare methods and stuff like that. Because the compiler is actually able to understand the math of these types. And that's the nice part. You don't have to understand all the category theory or whatever behind these types to actually be able to use them effectively. The compiler just handles it for you. So if you just have kind of the intuition of what they are that I've shown you here, that should be plenty to get going and just let the compiler do the rest. And also, these types are great because unlike when you you write a comment, you've seen all the memes and the jokes that go around about comments. We all know how comments go stale and they become lies. But at least they're co-located with your code, right? Whereas when you write unit tests, they don't go stale, but you have to go over here and read all this other code in order to understand this code. But when you can write your types, you can write them right there, right in the rest of your code. They're succinct, and the compiler and the next programmer, whether it's you or someone else, can understand them in the same way. So my encouragement to you is that if you haven't tried a language with algebraic data types, give it a shot, play around with it a little bit. Though I have to caution you, once you've done that, you may not be able to go back. It's kind of a dangerous step to take. I kind of messed myself up that way. But no, seriously, I believe this is something with real practical value. It's not just airy-fairy theory stuff. So you can contact me on Twitter or catch me afterwards. I'd love to chat some more, but have any questions at this point? All right, well, thank you guys for coming. Hey, thank you.
I'm going to miss your next one about the lambda calculus, but I really wanted to see it. Like, do you have the slides or anything? Are they up on the GitHub? Or?
Yeah, I'll upload them to the GitHub once I've done the presentations. So,
okay,
yeah,
sweet.
Yeah, and if the recording comes out good enough, it'll probably get posted.
Yeah,
too, so.
I have no idea how long that'll take, but
yeah,
it's really good stuff, man. It really is good when you start thinking about it that way. It's powerful stuff.
Yeah. Yeah, it was kind of neat because I was getting into all this stuff, and I have a tendency to get into this stuff and just go real deep and not explain it to anyone. Uh-huh. But I was forced to try to talk to my coworkers about it. And I was trying to tell them about functional programming and like how it was mathematical, but they were kind of like glazing over because like how could you do math on anything except for integers?
Yeah.
Well, the way you do math on things that aren't integers is with this. So
I liked how you're like, look, here's 1 plus 1, 1 times 1, and then it's like, yeah, but now why don't we extract out the variables and then get rid of the op? And it's like, the second you have that, you're like, okay, that was really easy to go from like really concrete to
really abstract.
You're like, that totally makes sense.
Yeah.
Like, why can't I do an operation on any two things? And why isn't that representation just as clear as 1 plus 1?
Yeah.
So that was really cool.
This stuff has been really eye-opening to me because I've just started to see like, wow, algebra is like way more generic than I thought it was.
Yeah.
And it really helps me to understand, like, it actually has helped me to really understand accidental complexity and how that happens, because if you kind of see that whatever you're working with already has this structure to it, you're just trying to draw out this structure.
Right, yeah.
So
how did you make the transition? If you've got I think you've got a couple minutes, but if you've got to go, just let me know. But how did you go the transition?
My next talk is right here, so I'm good.
So how did you go that transition from like A out B to like how you're applying it in your, daily programming? You know what I'm saying?
Yeah. So the first step for me was that I went to a talk actually at the Pittsburgh Tech Fest a couple of years ago where the guy introduced Haskell. So I played with Haskell a little bit, and one thing that really helped was I had a friend who already knew Haskell who walked me through a couple things. Yeah. But I only played with it a little bit. But then at my job, there was a tool I was using that was written in F#. So I just started to do open source contributions. Mm-hmm. So it was great because it wasn't, when you're trying to build something from scratch, it can be really hard to know how to get started. But like there was all these existing examples. So I would just like read through and see how he used stuff. Okay. And often it wouldn't be so much like I was creating a new algebraic data type. It would be like I was adding an element to one he'd already created.
Right.
And so I think that really helped me get off the ground.
So like now when you look at stuff, how do you look at things differently, or how does that, the fact that you're looking at algebraically, how does that translate? You know what I'm saying? Like kind of more of that practical. So now I understand like, okay, here's how you got to there, but now what's it look like from your view? You know what I'm saying? Like
right. Well, I would say maybe the most succinct way of saying it, I don't know whether you've heard this or not, but this is something a mantra that I've really taken on is make illegal states unrepresentable. So I always just, even when I'm writing C# now, I'm trying to think in terms of like, how can I structure my code that there's just no possible way for it even to get into that state. So that's just sort of the fundamental underlying thing for me now.
That's really cool. I probably should let you go.
All right.
My name is Greg Edwards, man. It was
Greg,
really nice
good to
meet you.
talk
That
to
was
you.
really good.
Yeah, thank you. I really appreciate it. I'm doing the next talk too. I submitted multiple talks to up my chance of getting accepted, and then they accepted multiple talks. So I was like, okay. Yeah. You know, that's funny. I did that in 20 minutes. I've done that talk in an hour before. It totally depends. It's really funny. I am the other speaker. Yeah. That was funny.
Everything from the last.
What's that?
Do you need to go?
Yeah, just go over again. That was funny because I had given that talk at Code Mash at an After Dark, and it was like an hour-long talk. And then I gave it at my company, and it was an hour-long talk again. So when I heard that I had to give it 25 minutes, I was like, oh man. So I cut out a few slides and combined them. And that was funny that like then that ended up being 20 minutes, you know? So yeah, all right.
Yeah, it was good. John's wife, she was like, I really like that talk.
Yeah.
She's so into coding. She's like, I thought I was going to be away from my head and actually like understood what he was saying. He's like, he
That's
spoke real
cool.
language. I really liked it.
Well, this talk came out of when I gave a couple talks at my work, and the only people who were really tracking with me were the architects, and they gave me some feedback of like, you need to break it down a little better. So this talk was like a really deliberate attempt to do my best to break it down, you know. So anyway.
And you know, like all the volunteers were on the channel this next time. There's apparently a hot spot. And he's like, can I sit in that way? Like, who can cover my duty? So I'm like, no, I want to stay there.
Cool.
So for like all the extra volunteers.
Well, I hope it's useful. I've never quite felt so much pressure to like really, you know, deliver on the value, because I'm like, man, all the money they paid to like get me here, and I have to be good. So
Better be good.
yeah.
No pressure.
Okay.
And then also, we'll just go right to 12 since it's lunch after this.
Okay.
Go over and see.
Okay. Sure. Who knows? This one might be 20 minutes too. Yeah. All right, the mic's still good? All right, well, let's get started then on the next subject. And there is a connection here. Another talk on math, another talk where I'm trying to maybe not give you the full mathematical rigor of lambda calculus. I'm not so concerned to have you be able to work it with all the mechanics of it, as I would like to just draw the dots for you between the calculus itself and functional programming. And if you're interested to go and learn it in a more detailed way, I'll recommend a resource to do that. But I think maybe the most helpful first step for a programmer is just to know where a lot of this goodness is coming from. If you've been enjoying the things that you've seen and heard at this conference, understand that like all of this really did start with the lambda calculus, and the shocking number of the ideas you've seen can be built just straight out of the untyped lambda calculus. So it really is your benefactor if you're a functional programmer. Actually, if you're not a functional programmer, it's probably still your benefactor and you just don't realize it. And this is maybe not the easiest thing to learn, but it is proper to distinguish between easy and simple, where easy has to do with how difficult it is for you as a person to grasp it, whereas simple has to do with the inherent nature of the thing itself. So lambda calculus actually is a simple thing, and out of it springs the whole of functional programming. So for any of you that weren't here in my last talk, my name's Keith Pinson. I'm a build engineer at Lucas Systems. And if you want to stop and ask questions in the middle, feel free. So if you've gone to any of the heavier hitting talks here, or even if you've just tried to read some stuff online, it can sometimes just be like, oh, I really want to learn this functional stuff, but it's like, why do I have to go through all this really rough math to feel like I'm really getting it? And that is a completely legitimate frustration. And I don't know what to tell you except for actually the struggle is worth it. So I'm gonna try here to maybe ease the learning curve on this particular thing as much as I can, and just tell you that I totally sympathize with the pain because I'm right there with you. I'm not someone with a super big math background in this stuff, and I'm not that smart. But before we actually start into it, it's always important to deal with why would we care? So I think these two diagrams are a great illustration of why the lambda calculus is actually simple. What you see on the right is an illustration of the way that a bar method on a foo object in an object-oriented language is able to, all the things that it's able to do. So it can take multiple input parameters. It can actually give output parameters, which are distinct from the fact that it can return. And usually in a lot of imperative languages, it can only return one thing, but it can return from different points in the function. It can also interact with the outside world without any special ceremony. It can just call out to your database under the covers. It can get data from there. It can write data out to anything that's out there. It can throw an exception. It can blow up. And it can not only blow up, but it can do it with multiple different kinds of exceptions from different places in the code. It can also read and write to the state of the parent object that it's attached to. And in some languages, it can even read and write to global state in your program. So when you go to look at a method, you don't necessarily have any idea what it's actually doing just by looking, at the signature of the method. Now, on the left, you have a pure language like lambda calculus. It should be immediately obvious how you can snap these together. And actually, there's a little bit of an imprecision in what I did here. Technically, I probably should have just put param into bar return. Because actually, though we do have a way that I'll talk about in a minute of representing functions with multiple arguments, it's even a little bit simpler than that. Strictly speaking, you only have functions with one argument, which might seem a little weird, but it leads you to a real place of simplicity. So you can see how here the model on the left is really going to offload a lot of mental overhead for you, because there's a very certain small number of deterministic things that can happen. And it composes. The only way you're going to compose anything on the right is by custom glue code. Now, because there's this underlying syntactic model that is just rock solid, underlying semantic model that is rock solid, the syntax can come out in several different ways, but the syntax ultimately ends up being an expression of the semantics. Like the syntax, of course, there are arbitrary pieces of syntax in functional languages, but what you'll find is languages based on the lambda calculus can often just arbitrarily generate different kinds of syntax. Like you can define infix operators, like a pipe forward operator, you can just define yourself. So that's syntactic sugar that's baked into the semantic model. And apologies to anyone if you're big on Ruby or CoffeeScript. My personal opinion is that's just kind of putting lipstick on a pig. Another thing that's really great here, and for any of you that were in my last talk, this dovetails well. It really helps you to kill accidental complexity. Because you saw all those crazy lines going around in my diagram on the right. Like, it's really easy in a language like that to make your solution more complex than your problem. But what you'd really like to do is be able to just pull your solution onto your problem as tight as a glove onto a hand. We sometimes talk about complexity if it's a bad thing. But actually, we love complexity. We wouldn't be developers if we weren't energized by tackling a complex problem. The complexity that we actually hate is when we have complexity that isn't managed well, or complexity that is there in our solution that really isn't inherent in the problem domain. And because of the simplicity of lambda calculus, it helps you to clean this up. And all of this kind of comes together in the fact that if you learn the lambda calculus, there will be some things that were just kind of mysterious to you about functional programming. They're just kind of like, oh yeah, of course. You'll much more easily find yourself working fluidly with it if you have at least a passing understanding of what lambda calculus is. So we can all have sweet moves like Napoleon. All right, so here is the grammar of lambda calculus. This is almost BNF except for line 2. So this is the entire grammar. Now, some people structure the grammar slightly differently, but I'm not trying to be too precise here. Basically, what you have is expressions. And an expression can either be some sort of name or identifier, or it can be a function, or it can be an application of a function to an argument. Now, I'm not going to give a strict definition of what a name is. In this talk, I'm going to just use single letters because I find that is the most clear. But you're a programmer, it's some identifier. A function is expressed as the actual character lambda from Greek, then some name, which is its argument, then a dot, which is just the separator between the argument and the body, and then whatever expression is in the body. And then to apply this function, and we use the term apply rather than to call, it's just the syntax is paren, then your function, then the expression you're applying it to, and paren. So to help your eyes get a little bit used to this syntax, which particularly when you start to throw a bunch of lambdas up on the screen, can be a little bit dizzying. I've just thrown up a bunch of different examples of lambdas from languages you might be familiar with. So the one on the top left is obviously lambda calculus. Then you have F#, Haskell, C#, Lisp, I believe, JavaScript, Python, and I believe that's Clojure there. My buddy helped me put a couple of these on for the languages I didn't know. So just take a good look at that, and maybe that'll help you to follow along a little better on the next slides, because I'm about to dive in with showing you some wacky looking stuff. So I do want to point out, though, that we've actually done something here which is sometimes counterintuitive, which is that we've stripped away a lot of features. We've said no to including a lot of things in the base language. Now this really does kind of seem to fit with some things John DeGose has been saying if you've watched any of his talks. But the idea is actually you end up in the long run with more power if you strip down your options initially. Because if you put too many things in initially, it can get hard to unify things together. Whereas what we have here is going to end up being something that just handles in such a smooth, unified way. It's amazing. And don't worry, we will get you the multiple arguments back, built on this structure. Now this is pure expressions, and I'm not going to try to argue dogmatically for purity. However, I do think it makes sense to not jump into discussing side effects too quickly, because just like having multiple arguments to a function, that can actually convolute what you're doing. So if you want to start with something simple, exclude sort of your edge cases to begin with, and then work on them when you get there. So we won't talk about side effects in this talk, but I just want to say that, like, really the nature of the guts of computing is the lambda calculus. You can deal with side effects in whatever way you want. Okay, so here's where the things get a little crazy. So if you have any trouble reading this, just holler out. What I'm doing here is I'm actually reducing the form. Now, I haven't introduced you to the formal rules of that, so just sort of accept the hand waviness of it. You can study those rules if you're interested. I don't think that's the most valuable thing for you at this point. Basically, what I have at the top is I've encoded a multi-argument function as single argument functions. So a function that takes an argument and returns a function that takes an argument that returns a function that has the actual function body in it. So this has allowed us to model all functions the same way. Multiple argument functions and single argument functions are really just the same thing. That's really powerful, because then I don't have to have two ways, or not two ways, but like infinitely many ways of handling functions based on the number of arguments they can have. I can handle all functions the same way. This also, though, gives rise to a tangential benefit, which if you actually start to write in a language that has it, you're going to fall in love with it pretty quickly, which is the ability to have partial application, because that's really just the opposite of doing this encoding of the multi-argument functions into single argument functions, which we call currying. So what you see on the top line then is this encoded 3-argument function being applied to 2 arguments one at a time. So first we apply the first one by passing in the a into the x, and the x that was in the body becomes the a. That gets you to line 2. Next we take the b and we pass that in as the y and substitute that into the body, and that gets you to line 3. Notice we still have an argument here. So we passed in 2 arguments to what we were considering to be a 3-argument function. And this has a lot of practical value, because this means that it's sort of like the command pattern in object-oriented languages, except for you have it available all the time on everything you have. Now, for any of you who have done some functional programming, I'd like you to shout out and say if you recognize some of these functions. So what is the first function? Right? What about the next one? It's not function composition. That's close, though.
Is it function application?
Yes. The apply function. What about the next one? And this one has several different names, so whatever name you want to call it by. Yep. You happen to pick the name I called it by.
Cool.
What about the last one? That's actually flip. So flip may not be something you're familiar with much unless you've written some Haskell, where you start to get real zealous about a points-free style. So don't worry about it if you're not familiar with the function. This is just to help you connect to a couple of basic functions in lambda calculus that you may have seen before. It's not intended to teach you all these functions. Here's where it gets interesting for us as computer programmers. You can actually build arbitrary data structures just out of this one simple little thing we've introduced. So to begin with that, you will see that we used we reused a function from the last slide and called it a different name, but we have a first function and a second function. Apologies for the typo there on that second line. And so it's just a matter of, if you apply 2 arguments, I'm going to give you the first one. The other one is, if you apply 2 arguments, I'm going to give you the second one. So then all we have to do is put together a function that we can partially apply 2 things to, and then can go around, we can carry it around as a packaged up version of the data that we can then either use the select first or the select second function to pull out the pieces of data that we need. So the bottom function is actually how you make a pair. You would invoke it on the 2 things that you need to make a pair out of. Then you have a partially applied function that is left taking the one last argument, and that argument will then either be first or second, which will then give you the element you need back. Does that make sense? That can be a little mind-blowing the first time you see it. Okay. The cool thing here is if you think about it, we could extend this to create tuples. We could do like lx.ly.lz. Or we could go another direction and we could start to nest these, and we could create lists. We could create tree structures. Actually, it turns out we can just build arbitrary data structures out of this. So it's true that it gets a little clumsy, like you wouldn't want to work with it at this level, but understand that this is giving you the foundation of the actual data structures you do want to work with. Because basically what we're representing here is the fact that you can encode arbitrary stuff into the lambda calculus. For example, we can just rename these same functions again and use them for a different purpose. If we rename first as true and second as false, then if we can just recognize that an if-then-else expression, so not like an if-then statement in an imperative language where you're actually doing something in it, but more like in an imperative language, like a C-based language like the tertiary question mark colon operator. So if an if expression is really just a way of pairing together the then expression and the else expression and then have some way to discriminate between them. So if we just consider select first to be true, select second to be false, and then we can pair stuff together in the if then else and actually execute whatever branch we need to execute by passing in true or false. Once again, I think this can be kind of mind-blowing if for no other reason than like you didn't even change the functions and now you're doing something that I think of in a totally different way. So one thing that was helpful to me as I was learning this stuff was when I stopped thinking of it in terms of like this is bool. Like I'm trying to like philosophically give the definition of like what bool is. Don't think that way. Think this way. We're encoding something that behaves like the Boolean logic we're familiar with into the lambda calculus. And then of course you can create all your other Boolean operators on top of this, which I don't have time to show them all today, but you can derive them all on this basis. Do you have any questions about that? I know this is a little crazy. All right, and here's where my mind really exploded when I first tried to learn this stuff. There's something called a church encoding, where we can actually encode the natural numbers into the lambda calculus. So the way we do it, because this is mathematically, and the way you want to, when you're doing something mathematically, and you just want an infinite set of things, is that you use mathematical induction. And what that means in this case is that we define something to be a zero. Now there's a couple different ways of formulating this definition. This is the one from Wikipedia, actually. Even though I've been using another book, which I'll show you in a minute for most of this stuff, I like the one from Wikipedia because you can sort of have an intuition of what the number is just by looking at the number of F's that appear in the body. So it's kind of just a convenient way of it being formulated that makes it a little easier for you to look at all this crazy stuff. So you define a base case, which is your zero, and then you define some kind of successor, which you can just keep applying on top of that to generate an arbitrary number. So it's an inductively defined set of naturals, and at this point we haven't encoded any negative numbers.
So it looks like the definition of zero is the same as the definition of false in your Booleans. Is that accurate?
It is, and that's sort of incidental. Like the other way of defining these doesn't treat it that way.
And it basically just means not
F.
Something it returns something that's a function that returns something that's not F.
Well, so don't take the Boolean stuff too much to heart because this is untyped. You can sort of give whatever, like you can just watch the way it behaves and then attribute whatever meaning you want to it, sort of. Do you know what I mean? So it's not like there's an inherently Boolean meaning there. It's a good question. Other questions? So, of course, now having defined these numbers, we're able to do unsigned arithmetic on them. And this is another reason why I like Wikipedia's formulation of this, because it kind of blows my mind. The fact that actually like plus is way more complicated than mult, and by the time you get down to exponentiation, it kind of almost makes sense in a really bizarre kind of way. But these are some of the functions then that we can define and do over these. And if we had a lot of time to actually go through a workshop together, we could manipulate these and show the way that they work. But the point that I really want you to take away is this. Just using these few simple ideas, we're able to generate all the programming that you're used to using on this one simple basis. So basically, we've unified your world of programming into one simple thing. Now, someone had brought up function composition before. This is actually the function composition operator. And I said this in my last talk, but I really think composition is the sweet spot in programming. I didn't include it in this slide deck, but one of the most beautiful pieces of code I've ever seen was from a talk at Code Mash, where a guy was demonstrating how to build a compiler, and he had some F# code, and basically his top-level code in his compiler was just his tokenizer function, or his tokenized function, composed with his parse function, composed with his check function, composed with his optimize function, composed with his, it was just like this huge string of functions composed together, and like you could literally see the architecture of his compiler by reading this one file of code. It was like so clearly like laid out what his design was. It was just amazing. And so I think this is another thing that if you start using a language that has it, you'll just fall in love with it. The ability to just arbitrarily stick any two functions together in general. And going back to that one slide I had with all the crazy stuff coming out, there's no way to generalize the combination of two methods in an object-oriented language, because you don't know what they're doing. So you don't know if you got all your wires connected. It always takes a manual glue or the recognition that you might have missed something. But this is a completely generic way of taking any two things in your language and putting them together. And remember, we've defined data in terms of this. We've defined the operators you're used to working with in terms of this. We defined functions in terms of this. And you can just take these things and put them together generically. That's really powerful.
I'm not quite sure how to read this notation. So in this example, what's the body of LambdaF?
Okay, thank you. I think I missed out my dots in this slide. So this is a function encoding a 3-argument function. And so the body, it reads like this: a function that takes in two functions and an argument and applies the second function to the argument, takes the result of that, and applies the first function to the argument.
So the missing dots
are between F and L and G and L.
Okay.
Yep, sorry about that. Thank you for that question. Any other questions about this? So if I piqued your curiosity, my recommendation is don't go read Wikipedia unless you're a masochist, even though they have a good representation of church encoding. That's what I did. And is there a question back there, or are you just raising your hand? Okay. That's what I tried to do when I first tried to learn this. And first of all, it didn't help me to know how to use it in programming. And second of all, I was like bouncing my head off the wall trying to make sense, because Wikipedia gives you everything in a very compact form, not in a tutorial form. So I've, however, studied this book some, and I found this book to be really helpful, because what he actually does is he starts from just the basic functional programming. He actually teaches you the mechanics that I sort of just breezed over here. And he has lots of examples, and he has exercises at the end of the chapter. But what he does is he builds up to an entire full functional programming language by the end of the book. And something that I didn't show you that he does is he actually even introduces a concept of types and is able to encode some types with this. Now, it's not runtime enforced types, but he's able to actually build that in as well. So this, in case you have trouble reading reading the slide because I know the font is kind of narrow. This is an introduction to functional programming through Lambda Calculus by Greg Michelson. So a helpful book if you're curious to explore more. I hope, though, that even just what I've showed you may give you enough to help you feel a little more comfortable with why certain things, like the function compose operator, where they come from in functional programming. And so I really would emphasize to you that because the Lambda is the foundation of all the benefits you're reaping that you've heard about in all the different talks at this conference, that if you are able to just take that grind and go a little further in learning it, you don't have to become some sort of expert that can manipulate these things in your head. But if you just work on it a little bit, I think you will find that there's payoff when you then go to program. So that's what I have. Do you have any more questions? All right. Thank you, everyone.